Welcome to Math with Michelle, where math finally makes sense. Whether you're tackling high school math or diving into college algebra, I'm here to break it down step by step with real examples and zero stress. From algebra to functions, graphs to equations, I've got it covered. Hit that like button and let's master math together. Welcome to indefinite integrals and net change theorem. When we're talking about indefinite integrals, we're talking about the integration of f of x dx. These cannot be put into your graphing calculator. You're not going to get numerical answers because we want to know not the area under a curve between A and B. We're just wanting to know the equation that if I wanted to find the area under the curve, I could. Or, hey, this is the derivative. What was the equation originally? So we're usually going to say that this equals cap f of x. Okay? In other words, f of x is equal to the derivative of cap f. So make sure you just kind of understand whether they're using capital and lowercase or they're using capital and capital with the tilde mark or what. So just some rules to know. Anytime you have a constant multiplied by your f of x, it's the same thing as having the constant multiply by the integration of your f of x dx. Okay. And another simple one that we're going to look at, if you have two things being added together, it's okay to change them into the format of the integral of f of x dx plus the integral of g of x dx. And sometimes this looks like an S sign, and I try not to make it look like an S sign. It's really a elongated, like special S thing. It's super tall. You kind of notice it a bit more in my other videos that it makes a weird little, like, I don't know. Super tall doesn't really look like an S on the calculator. Okay, so the calculator can only do definite, and these are indefinite or infinite, right? So we're going to look at some examples, and we're going to look at the numerical versus the rule. So let's say you had the integration of k dx, or for example, the integration of a number dx. Well, anytime your answer was just 5 was the derivative of some equation that was linear, right? Because it always had a slope of 5x plus something. So see how if I derive this 1 times 5, drop off the x. So, wow, hey, that decided to just go blurry all of a sudden. So now we're just making it a formal rule that says, hey, look, anytime you have a number and you're going to integrate it, it goes back to the equation k times x plus c. And I find that that's one that pretty intuitively everyone kind of catches on to. However, something such as x cubed dx, you might have had to think about it, right? What did that go back to? Well, x cubed we know is the derivative of something to the 4th power, but if I put a 4 out front and rederive it, then I would have 1/4 x cubed, so I have to cancel that out. Now if I move the 4 out front, the 4 here and the 4 here, when you derive, would cancel each other out. So that gives us this rule right here. The integration of x to the nth power dx is equal to x to the n plus 1 over n plus 1 plus c. And the plus c happens because we don't know if there was a constant there before. That kind of drops off, right? Now note, n cannot equal -1. Because -1 plus 1 is 0, and now that doesn't work. We would have an undefined denominator, so this does not work for n to the -1 power. N to the negative, what was that one? Well, let's think about that. So we need to do the integral of x to the -1 power dx. Okay. which is the same thing as saying the integral of 1 over x dx. And there's not really much better I can do for a rule on this. We're just going to have to go straight to it. If you remember 1 over x was the integration from natural log. And again, that plus c is still coming back. There's not much else you can do for that. You just have to know that one. Okay? Kind of like the integration of e to the x. Well, e to the x derived to e to the x, if you remember. So the integration of that is e to the x plus c. But what if it wasn't something else? Let's think about this. So let's say y equaled 5 to the x, and you had to find plus 9. We'll just do plus 9. And you had to find the derivative, right? It would be the natural log of 5 times 5 to the x. That would be your derivative. So what if we're starting off with the integral of 3 to the x dx, and we want to go back up? This is the derivative, and I have to go back up. Well, going back up, we would have 3 to the x plus c, but when I derive that, I'd have that natural log of my base, so I'd have to cancel that out and have that. So my integral of a base to the x is b to the x over the natural log of b plus c. And again, that plus c is because there could have been a constant at the end. So these are kind of all intuitive rules that are just kind of good to know that you can do with your practicing. Okay? So what we're doing is we're just taking and working backwards. So let me give you just a whole list of a bunch more that might pop out at you. Your derivative rules, right? The integration of sine x dx goes back to negative cosine plus c. However, cosine was the derivative of sine. Secant squared was the derivative from tangent. Cosecant squared was the derivative of negative cotangent. Secant tangent was the derivative of secant. Cosecant cotangent was the derivative of negative cosecant. And some of these you can work out by changing them back into sine and cosine terms and things like that. A couple of them that you can't, and you have to be really careful with, is the integral of 1 over x squared plus 1 dx. And that goes back to and the integral of 1 over so arcsine and arctangent. And there's a plethora of rules out there that you can just memorize when it comes to trig features, but not necessarily something that you have to have down immediately, but flashcards are a great thing. So let's just go ahead and let's just throw some of these rules into applications, because that's the only way to get practice with these, because they're all going to look different but yet not be different. So the integral of 10x to the fourth minus 2 secant squared x dx. So technically, you're kind of supposed to think about this like this. The integral of 10 times x to the fourth dx minus 2 times the integral of secant squared x dx. That way you can apply it directly to a rule. Okay, so the power rule, 10 times, we're going to increase that power by 1, and whatever we put up top, we divide by. And I could put a plus c on each of these, but if I have a constant on the first one and a constant on the second one, they're just going to add to a bigger constant. So I'm going to put a plus c at the end. Minus 2. Now, if you remember, secant squared is the derivative of tangent. I'll put a big plus c at the end. So we can simplify it to 2x to the fifth minus 2 tangent x plus c. Okay, so cosine theta over sine squared theta, d theta. Now, right now, you only have one way to do that, and that is by playing around with our trig. So we can change this to cosine theta over sine theta multiplied by 1 over sine theta d theta. Notice I'm writing the integral sign every time. So cosine over sine, that's cotangent, minus, or times. And 1 over sine is cosecant. Now we had a rule for that, cotangent times cosecant. We did have that rule, and that came out to be negative cosecant theta plus c. All right, so let's take this and put it back with that fundamental theorem of calculus. The integral from 0 to 3. Oh, now I have a definite integral of x cubed minus 6x dx. And that will give us to the 4 over 4 minus 6x to the second over 2. From 0 to 3, I was able to not write plus c's because I had my upper and lower bounds. So 81/4 minus 27 from the first part, and 0 from the second part will give us negative 6.75. Much earlier than easier than when we did this particular problem a few videos ago, where we actually did it using summation notation. So, okay. All right. So here, 0 to 2 of 2x cubed minus 6x plus 3 over x squared plus 1 dx. Okay, so this is the power rule here and here. We can use the exponent rule on both of those. But what about that last one? Well, if you'll notice, that last one looks like we've just taken this fraction and we've multiplied it by 3, right? Or I can pull that multiplied by 3 out front. So that gives us a 3 tangent. So that's that arctangent rule. Okay. So 2x to the 4 divided by 4 minus 6x to the second divided by 2 plus 3 arctangent. We're going from 0 to 2. Okay. So if I substitute 2, well, here, let's reduce this. 1/2 x to the 4th minus 3x squared plus 3 arctangent. Okay. So 2 to the 4th is 16 divided by 2 is 8 minus 12 plus 3, whatever the arctangent of 2 is. minus 0 minus 0. Let's double check the arctangent of 0. I'm in radians. It's 0. So that will give us 3 arctangent of 2 minus 4. And that would be an exact answer. I wouldn't expect my students to go ahead and find a number for the arctangent of 2, because it is not a nice number. Okay, so again, you're in calculus. You're trying to do this by hand because your calculator, or you're prepping for that AP Calc test that does not allow you to use a calculator on the first part of it. And you've got something like this. I mean, throw it in a calculator if it's multiple choice, then we don't have rules for quotients. We just don't. Okay, so we're going to need to rewrite this as powers all the way through. Why does my camera hate me today? Okay, so the first thing I'm going to do is I'm going to say we've got the integration from 1 to 9. But I'm going to divide everything by t squared. Remember that this is the same thing as having a t to the negative second. So I'm just going to distribute. 2 plus t to the 1/2 minus t to the negative 2. Now I can apply the power rule all the way through. Okay? So 2t plus t to the 3/2 over 3/2 minus t to the negative 1 over negative 1 from 1 to 9. Okay, so let's clean that up. 2t plus 2/3 t to the 3/2 plus 1 over t from 9 to 1. Okay. So we're going to do 2 times 9 plus 2/3, 9 to the 3/2 plus 1/9, all of that minus 2 times 1, 2/3 times 1 in any power plus 1 divided by 1, right? Okay, so in case you don't love these numbers, right? Okay, so 36.1 repeating, right? This would be 3 2/3, right? So minus 3 2/3, 32.4 repeating. Okay. Or 292 over 9, or 32 4/9. Any of those are acceptable and are going to be the exact answer. So make sure that you're really, really comfortable with that exponent rule, okay? Know when you can use it. And again, we're not talking about anything with deriving or things like that. So, now, net change. Because I did say we'd talk about net change, right? When they ask you about net change, integral from a to b, f prime of x dx equals f of b minus f of a, quote unquote, the area under a curve, right? But let's say I give you velocity and I give you the equation. Well, if we go back up and we integrate velocity, don't we go back to position? So when we integrate it over an interval, our net change would be our change in location, right? So That's what we're talking about with net change. So you have a particle, and it's moving along a line. So that its velocity is represented by an equation. In our case, our velocity is going to be t squared minus t minus 6 in meters per second. Find its displacement over 1 to 4. So basically, I'm wanting to know how far does it move between 1 second and 4 seconds. Okay? So it's displacement. That's an important thing to look at. So we're going to integrate from 1 to 4, t squared minus t minus 6 dt, t cubed over 3 minus t squared over 2 minus 6t, 1 to 4. And in our calculators, we're going to type 4 to the third divided by 3 minus 4 squared divided by 2 minus 6 times 4 minus 1 to the third divided by 3 minus 1 to the second divided by 2 minus 6 times 1. And you're going to find out negative 4.5. Or left 4.5 meters. So between 1 second and 4 seconds, it has moved left 4.5 spaces. That doesn't mean it's only moved 4.5 spaces. It's just that its net change is 4.5 meters to the left. So here's what we have to keep in mind. Remember this factors to t minus 3, t plus 2. So 3 and negative 2. It has positive velocity, negative velocity, positive. So it's moving right, then left, then right again. Okay. Well, what if I wanted the actual distance traveled? Okay. What if I wanted to find the total distance traveled? Not the net, but the total. Between 1 second and 4 seconds. How would I do that? Well, now most of our time is spent going to the left, but what we'll do is the absolute value of the integration from 1 to 3 plus the integration from 3 to 4. That way we find the actual distance total moved, okay? So we already know the integral, right? But we just have to go ahead and do the math with it. So I'm going to use this. I'm just going to use different numbers, right? So we'd have t the cubed divided by 3 minus t squared divided by 2 minus 6t from 1 to 3. I want to make that positive, plus t to the third divided by 3 minus t squared divided by 2 minus 6t from 3 to 4. And again, we want that absolute value. So to save myself a little bit of time, I'm going to pop into here, x to the third divided by 3 minus x squared. I forgot my divided by sign. Divided by 2 minus 6x. And I'm just going to calculate the value. What is my window? Oh, hey. Let's go negative 10 to 10 again. And I'll just go to my table. Make sure my table setting's where I want it. Okay. 1 is negative 6.1 repeating. 3 is negative 13.5. Okay. So then we'd have 4 is negative 10.6 repeating minus, and 3 was negative 6.16 repeating. And if you type that into your calculator, you'll get approximately 10.17 meters. So again, the reason why this number is bigger than this number here is because this is taking our leftward direction and making the absolute value of it, and then our rightward direction, so that we can see how far we've actually traveled, not our net change in position. Okay. If you ever do get stuck doing these, you can go back to your rectangle method that we have gone over, where you look at the summation rules. But a quick note, let's say you have an f of x equation and a g of x equation. And you want to find the area between them. And this might happen because you might be trying to find like the area of something on the ground from an aerial photo, and you made one equation for the top part of it and one equation for the bottom part, or something. Maybe it's like a pond, right? And you need to find the area in between the two. Well, what we can do is we can kind of lift those off, right? You have your f of x, and you have the area under it. And then you have your g of x, and you have the area under it. And then you have blurry. If we were to take the entire area under f of x and subtract the area under g of x, what's left is just this section. So anytime you want to figure the area under an area between two curves, you're going to do the integral of your upper curve, minus the area of your lower curve. And you'll be able to find the area in between two curves, which then leads into some more stuff that you're going to see in Calc 2 once we start rotating things around and revolving 2D images to get 3D images. So there's fun stuff that this is going towards. We just haven't quite got there yet. Thanks for learning with me here on Math with Michelle. If this helped, give it a like and don't forget to subscribe for more clear and simple math lessons. Got a question or topic you want me to cover? Then drop it in the comments. Until next time, keep practicing, stay curious, and remember, you've got this.